Alright guys, this is the chapter 11 section 2. This is the difference of two means from a dependent sample. So we know it's from a dependent sample because we're dealing with fathers and sons. They depend on each other. We're going to be looking at the mean difference of father's heights and son's heights. So when we look at this, we need to make sure that we're doing a dependent samples. It's kind of like another example of dependent samples would be, do husbands and wives have similar IQs? So when you look at the IQ of the man and the IQ of the woman, you're looking at the difference between them because this husband matches up with this wife. Because someone IQ could be a 120 and they're married to a 115. Or someone could be an 80 and they're married to an 82. So you would think the similarities between spouses would be the point of interest. So again, dependent sample. Another example would be like a pre-test and post-test because the same person would be doing it. These I was working on with someone else. So let's look at this one. So that fathers who have adult male children records the heights of both the fathers and the sons and obtains the accompanying data. Are sons taller than their father? And so let's notice that the difference is our y values minus our x values. So y's, they're considering sons, fathers is x. So we have this data, but we have to figure out our null hypothesis, an alternative. So whenever we're doing a dependent samples, we're looking at the mean difference between our numbers between the x and the y. So our null hypothesis is always going to be that the mean difference is equal to 0. Now our alternative we have to figure out, it says are sons taller than. So that means the y value is larger than the x value. So if we do a y minus x, we should get some positive number. And that would lead us to picking this one, some larger value. And the next part, we actually have to find the p-value. So we're going to take our data and we're going to bring it up in StatCrunch. And we're going to t-stats. And we're not going to go to two sample like you would maybe think. We're going to go to paired because they're dependent. They are paired up. So we have paired data. Now remember when we put this in, it was our mean of the sons minus the mean of the fathers. So we have to be careful how it's notated. We could save the differences if we want. We really don't need to. And we said that the mean difference would be greater than 0 because we had sons first and fathers second. And if we compute, here's our p-value of 0.3713. 0.3713 and 0.371 to 3 decimal places. Now we're going to make our conclusion. Since our p-value is greater than our alpha, we do not reject. If we do not reject, there is not sufficient evidence. So do not reject, not sufficient evidence. Alright, now here's the one that I was working on earlier that I missed. It is just inputting the data, but I think the way we have to input it is something we need to be careful about. So here we're just making a confidence interval between some dependent data. It says that equipment using steel ball indenters. So it's a hardness test. The manufacturer thinks it would be better to use a diamond indenter so that all types of metal can be tested. Because of differences between two types of indenters, it is suspected that the two methods will produce different hardness readings. They're tested, the metal specimens that they're testing these indenters on are large enough so that 2 indentions can be made. So that means each machine indenter is being tested on the same specimen. That's what makes it dependent. So when we go to make our confidence interval and we put this into StatCrunch, what I was doing incorrect earlier, again, T-stat paired, I was putting steel ball first and diamond second. It really doesn't matter as long as we can interpret the confidence interval. But as far as what my math lab, my stat lab wants, they want diamond first and steel ball second. That seems to be a trend. And then we're doing a confidence interval, and they said 95%. So if we compute this, we'll get, I think they said rounded to 10th place, so a 0.2 to a 2.9. So a 0.2 to a, whoops, 0.2 to a 2.9. And so if you had negative 2.9 to negative 0.2, I wouldn't consider that incorrect. It's just not the way they're reading it here. And then state the appropriate conclusion. When we're looking at this, is 0 in our confidence interval? And it is not in our confidence interval, therefore we do have sufficient evidence to conclude that the two indenters produce different hardness readings.